Good. Oh, yeah. 7-5 bucks. Oh, she was going on. I just didn't have that study guide.
God. The question I got wrong on conduct of ops quiz was a typo. Okay, how much time did I waste on that typo? A little bit. All of the above, because it shouldn't have said intuitive control room geometry. It's supposed to say unnatural control room geometry. It's a hell of a typo. It's like calling Jen Marcus or something. It's just, how could you do that?
I don't know, we're about the same color. He's a little hairier than me. Or
You are,
I guess maybe.
you're both pinkish for sure.
Yeah, we're pinkish.
The hair's about the same color too.
Yeah.
I guess that mistake could easily be that.
Yeah.
Good.
He's only like half a foot taller than me. 100 pounds lighter.
How many times did you dress like Kermit?
Like,
Kermit?
Kermit?
Yeah.
I haven't had an opportunity, but I had an opportunity. So that's,
Like, fourth the way they.
I think you got to saw another,
oh, what?
another Oscar the Grouch coat.
If you drive Marcus with the cape, you'll come away with Andrew and seeing this.
Really?
Yeah, no, it's 100% true.
Like, can it be a store-bought cake?
I don't think Marcus is taking it.
Store-bought cakes are pretty good sometimes. They're charging up money for them.
Yeah, you missed that last semester. Marcus came and serenaded everybody. Mike walked into the class, like looked for a half second and just walked away.
What happened? Did you fall down? Are you so great?
How did the test go?
I needed to look over what it means.
Are these like cute days?
I looked at it,
They're like 3 months.
looked up, I was like, oh, like,
I need to do it.
we only have 90 minutes to take it. Stop down the computer.
Yeah,
Thank you.
yeah, no problem.
Does anyone else come in that wants a print? They're over here on the bookshelf for now. If you want a paper print.
Yeah.
Thank you. Okay.
Mike's this. You're bad.
No. It's a big ball.
Oh, yeah.
You're ready for this explanation on that question.
That and a couple other things I'm ready.
All right, guys, let's go ahead and take attendance and see if anybody's missing. And today we're going to talk about STEAM tables, and then we're going to talk a little bit about the exam next week and do a little bit of a review. So let's see here. Okay, Caden?
Yeah.
Okay. And Connor? Okay. Jonathan?
Here.
Awesome. Joe?
Here.
Okay, Marcus?
Here.
Porter? Great. Cattell? Okay, Lynette?
Here.
Okay, Sam?
Here.
Okay, Ethan?
Here.
Okay, Wiley? Okay, great. Jack?
Hello.
Hello. Kyle? Denton?
Here.
Okay. Amber? James?
I'm here.
Awesome. Rodney?
Here.
Okay, thank you. Jennifer?
Here.
Okay. Rock? Okay. And Haley? Okay. Okay. So if you have your textbook, if you would open up to page 241, there's over the next few pages some sections of a STEAM table that are on that, and I really prefer the way that they're laid out in the book. If you don't have your book with you, I have a couple of STEAM tables in Moodle that you can open up. So if you go to week 4 under Thursday, there's a couple of different STEAM tables. Let me share. You guys can see. So we've got English and SI units here, and then we've got some for saturated steam. Let's open them up. So English units, SI units, saturated steam. So if you go in here, this English unit, it has this list of tables in the appendix, right? And so depending on if you're dealing with saturated liquid or superheated steam, these tables A11 and 12 are going to be steam tables. And if you go through here, right? So here's for our saturated refrigerant. It's at a specific temperature and pressure. And then it's going to tell us the specific volume, internal energy, enthalpy, right? So this is essentially an example of a steam table. They can be laid out slightly different ways if you're looking at your textbook, right? It has a pressure, right? So on page 241, it says atmospheric pressure. And then it has saturation temperature is 100 or 212 or 250. And then it has a list of different quality percents for the steam. And then from there, you can determine the specific volume, density, enthalpy, entropy, etc., for the pressure and temperature and quality of water that you're looking at. So they're each kind of laid out just a little bit different based on the information you're actually trying to find. So here we have for our other units, our SI units, and the saturated tables, table A, 11, 12, and 13. Hi, Kyle. Thank you for letting me know. I will change your attendance. But we can scroll down here. And for a given temperature and pressure, here's our specific volume, internal energy, enthalpy, entropy. And then here, this is a little bit simpler table, right? So this is telling us it's for saturated steam, right? And we have that saturated steam at a specific pressure and temperature, right? And because we know we're dealing with saturated steam, that pressure and temperature are going to be, given as they relate. That's how we get our saturated steam. And then we can get our heat of the liquid, latent heat of vaporization, total heat of the steam, specific volume. So this table is just giving us slightly different layout. But what's really important about steam tables is they allow us to make important distinction between the properties of the steam in different thermophysical states. So as we look at our subcooled or wet steam or our dry steam or superheated steam, whatever it is that we're looking at, you can look at the different table and determine all of these different parameters. You can look at a graphical representation of this. So for example, in the textbook on page 245, there's a pH diagram for water and a TS diagram for steam. And in these PDFs that I have on Moodle, you can go right here. Figure A9 is a TS diagram for water. So we can look at the same thing online. So here's a TS diagram for water, which looks just like figure 7.19 from the textbook. And you can trace your temperature and your different pressure lines, and you can find, where that interacts with different specific entropy, and you can do it graphically, right? So I've got temperature here, we've got enthalpy here, and then we've got different pressures on these lines. And I can trace that, but we put it in table format where it's much easier, in my opinion. Table 7.3 in the textbook, and then the tables A11 and 12 and 13 on these online PDFs. And it gives us that information in a much easier to digest format, right? I would much rather look at this chart for a specific pressure and temperature, look at my temperature, volume, enthalpy, entropy, internal energy, etc., than trying to trace it on a figure that looks like this, right? This is a much more complicated and error likely scenario. So I want you to have seen the steam diagrams. I want you to understand that by charting this information experimentally, we were able to put the tables together, but I'm only going to ask you to read information from the tables. I'm not going to ask you to look at Mollier diagrams or TS diagrams for water and pull out entropy and stuff. So just so you kind of know the expectation in class. But we are going to do a quick exercise. It's working through an example in the textbook for using the STEAM tables. They're a very valuable resource. The example problem, is talking about their use for nuclear engineers, but they're also extremely important for operators who are going to be interacting with systems that have steam, water, or a steam water mixture. So their example is a PWR at a pressure of 2,250 PSI or 15.5 megapascals. This example is on page 244 of the textbook. Okay. So liquid water enters the core at 295 degrees Celsius and leaves at 335. What's the difference in the specific enthalpy of the water entering and leaving the core? So essentially what it's asking us to look up is specific enthalpy, H, for water at 15.5 megapascals and 295 degrees Celsius. So we need our table for steam. Water enters. So and I'm not sure if these online ones will have the exact pressure and temperature we need to look at. It doesn't look like they go high enough. So those of you with the textbook, 15.5 megapascals. On which page of the table?
243.
243, that's correct.
Middle.
And our temperature that we're dealing with is 295, right?
Yeah.
I know. That's what I've been doing. Makes no sense. Over here is your 295 Celsius water, but that's at a different pressure.
So we want to find our specific enthalpy of the water entering the core, right?
Yes.
So how do the percentages come into play, or like the quality?
So from the DOE handbook, there is an equation for quality. I think there's one in the textbook as well. Essentially what it's saying is what percent of the mixture is water and what percent of the mixture is vapor. Okay, so quality, yeah, if you look on page 235 of the textbook, it gives you essentially its quality is the ratio of vapor to the liquid. Okay. Half the mass of the mixture is liquid and half of it is vapor. Then our quality is 0.5, or it would be 50%. Right? So at essentially 5%, you're almost all liquid, and at 90%, you're almost all vapor. Does that make sense?
Small part of it makes sense.
Part of it makes sense?
That part.
That part, okay.
Part about the water quality makes sense.
The question.
Yeah. I couldn't tell who said they have a question, but go ahead.
This is James speaking.
Okay.
Are we looking for our saturation temperature? Because that's 8 MPAs versus our 15.5 MPAs, which has a different saturation temperature.
Right. So essentially, because we know the water is water when it enters the core, right? And then it's going to be increasing in temperature at that specific pressure, right? So we're going to look here. Saturation temperature of 100 and so I see what you're asking. It gives us this 15.5 megapascals, and we look at that on page 243. It says the saturation temperature is 344. So how do we find out what our enthalpy is for the water coming in the core? Because that's at 295, right? Is that what you're
Yeah,
asking?
that's correct.
Okay. So if you look on this table, we have 295 degrees Celsius.
Joe, were you able to find the value that was on this page on the other one?
Which value? Pressure?
No, this, enthalpy, that's one of the
Oh, no, that's not.
value.
335. And 12, 14. So let's look. It looks like I'm trying to bring this up to show you guys in computer, because I know if I hold the book up, it won't show very well.
Because I see these two values, but I don't see them on the other page.
But you're going to have a specific pressure and temperature, right? So if on the diagram on page 245 that's not in table form, you'll see, right, where we have a temperature of 295, which is almost 300, right? And then we have our pressure of 15.5, right? So if you take where that roughly intersects, we're going to be able to see our enthalpy, 15, that figure 7.18, it goes across all the different enthalpies and is with a temperature. So essentially, what it's asking you to find on the table, right, is that we have, so we're going to be at one of our very low qualities because it's going to be almost all water coming in, and then it's going to leave at 335. And so if we do this at a saturation temperature of 335. It looks like they don't have a table one right on here, but if we did our 15.5 megapascals, our liquid water at low quality, because it's going to be liquid water, and then it's leaving at 335, which is just below our saturation temperature, right? So it's going to still be water. It's not going to be saturated steam because of that. The saturation temperature, it says on page 243, is 344.8 degrees Celsius, right? We don't ever hit that at that pressure, right? We stay at 335. So we're never going to be saturated steam. We're going to need to be looking at essentially it's still liquid. So because of that, it's giving us this table, right? It looks like if you look on page 241, because we know we're still water, then we actually have to look at Appendix G to get the correct table for water. Okay. So table G2, we've got our pressure between 1 and 22. It gives us what the saturation temperature would be, right?
Can you repeat that last part?
Pressure.
So that makes sense that the sections they put in the textbook in table 7.3, because this is for wet steam and about liquid water entering the core, we actually look section of the steam table that's in the appendix. And table 7.2 tells us where we can go for our water. Subcooled water is at F and saturated water is in appendix G.
I think it's in the back of the book, 1313.
Yeah, it is in the back of the book. Did you say you found it on page 1513?
1313.
1313. Okay. Yes. That's where I'm looking. So appendix G starts on 1313. And table G2 is got the 1 megapascals to 22 megapascals, right?
So Mackenzie,
Yeah.
I have so to get this enthalpy, do you have to extrapolate between the like 14 and the 16 to get it? Is that where that
Essentially,
number?
yeah. You wouldn't be very off to say 15.5 can round up to 16, but when you read the value that's there, it's a little bit off from what they write in the solution to our example problem, right?
All right, so they just use like an extrapolation formula to get that.
Yeah, which we could also look at the picture, right? Something like figure 718, and we could actually look at where our point is on the graph. But because we're dealing with 15.5 and the table has 14 megapascals and 16, and you are looking for your
It has as a liquid, so HL.
Sorry, say that again.
So there's three specific enthalpies, And I'm assuming HL is the enthalpy as a liquid.
Correct. That's correct.
Is that the one that we want? Because it's
Yes. What page did you find that one on?
that's just the next page over.
1348.
So for liquid water, I see that the correct appendix page to look at is going to be page 1309. I'm going to look at, and this happens to be for water at 15.5 megapascals. And then there's a temperature of 295. And you follow that line across. And what is the specific enthalpy?
1310.6.
Yes, right? So we have our liquid water coming in the core at that pressure and temperature, and that gives us 1310.6, right? Now, when we are leaving the core, we're at 335 degrees, right? And we're still a liquid, right? We haven't become vapor. They haven't told us anything about quality. To look at the tables on page or back in chapter 7. So now our water at 15.5 megapascals, we're going to follow that temperature down to 335, right? And what is our specific enthalpy?
1552.
1552. And in the example problem, they have slightly different decimal points. I'm going to guess because that they actually looked at the figure and tried to get exact. But from our table, this is more than close enough. And so the difference would just be that 1552 minus 1310, right? And that's our difference in enthalpy for those two states. Because we're past the saturation temperature, we never change the steam. So we're looking at a steam table for water. If we went over to Appendix G, we would have that saturation temperature has been reached, right? And so now we have our mixture of saturated water and steam, okay? So it's going to have different temperatures that mixture will occur at, and it's going to tell you what that saturation temperature is, okay?
Mackenzie, which
Given pressure and temperature, you'll have that mixture, and you can look up the volume, internal energy, enthalpy, etc. And if you turn one more appendix over to H, we now have superheated steam, right? And so we're going to have, they just selected 4 and 8 megapascals is the, and I think 6, yeah, between 4 and 8 are just the pressures they selected to show you pieces of the table at. And you're going to have a pressure, so table H1, and you'll have the temperature that you can be a saturated steam at that pressure. And again, you'll get density, volume, internal energy, and all of these properties. So as we said in the beginning, the tables can be arranged slightly differently based on the information you need. And they have in the appendix subcooled water, water vapor, saturated mixture, and then your superheated steam for a couple select pressures. Does everyone follow how we looked up the specific enthalpy of the water at 15.5 megapascals and 295 degrees and 15.5 megapascals and 335 degrees?
Yeah, with the right table, it makes sense.
Yes.
Mackenzie?
Sorry, I had just assumed when I saw this table in here that they made it easy in the reading for us to do this example right in the reading. I didn't,
No.
that table 7.2 to see that it told us to skip to different appendices. It looks like they have wet steam and dry steam in there too.
Mackenzie, I have a question when you have a moment.
Sure, go ahead.
Okay. Basically, that example problem 7.5, which is a quiz question also.
It is.
How, I still don't understand, how are we to know what appendix to look in or what table to look on?
Okay.
I wouldn't know where to look to find that information. Neither the question on the quiz nor the example problem seems to say where to go. And I'm
That's
wondering
true.
how.
So one, if there is a test question where I have you look at a steam table, I'm going to give you the steam table that you need to be using. So it's not my intent to necessarily purposely try to confuse you. But what the textbook is doing here is it essentially says, in the reading on page 240 under that section 7.27, okay, this last for the list. 5 property tables are required to describe the thermophysical properties of water and steam. These property tables are 1, a subcooled property table for subcooled water, saturated for saturated water, wet steam for the saturated water steam mixture, dry steam table for the saturated steam, and then a superheated steam table for superheated steam. So there are 5 different categories of steam tables, whether you have subcooled water, saturated water, wet steam, dry steam, or superheated steam, right? So those are our 5.
So would it be fair to say that we should have been looking in the appendixes the whole time to solve that problem, the quiz problem?
Yes. Yes. That quiz question, I believe that when I wrote it, I said specifically using the steam tables from the text.
Yes, you did.
Yeah. So,
Right.
so what you should have gotten in the reading is on table 7.2, it essentially tells you they have small sections of the subcooled water steam table in Appendix F. They have selected physical property sections of the saturated water table in Appendix G. They have table S3 has wet steam, and Appendix H has dry steam and superheated steam. So that table 7.2 is essentially telling you, here's where we have parts of the steam table for you to use in this book for each of the 5 types of water and steam that we're going to need to look at. And so then when you read example problem 7.5, and it tells you, hey, we're looking at steam tables, right? Steam tables are one of the most important resources. And we have this pressure and temperature liquid water, and then this pressure and temperature liquid water. Find the difference in specific enthalpy. You should say, okay, hey, I have liquid water at a temperature above which it normally boils, being held at a pressure. So then I know that I need to be looking at liquid water. And so I'm going to go back here to the appendices where we have information from our selected parts of our steam table. And I know that I don't need to look at Appendix H because that's superheated steam, right? And we're not talking about steam, we're talking about liquid water. So then I can go to my subcooled water, right? And say, hey, I'm at 295, I'm still water. That gives me a specific enthalpy of 1310. And then I'm still water at the second temperature, right? Which was 335. Okay, so on the same table, subcooled water, temperature of 335 at the pressure of 15.5 megapascals. Okay, here's my 1552 as my specific enthalpy. So it's understanding that what we talked about today is that there's different tables for the different types, essentially, of water that we can have: subcooled, saturated, and then, of course, wet, dry, and superheated steam. Today's lecture was supposed to show you that you need to know what phase you're dealing with to know what table to go to.
So it would be Appendix F in this particular case?
Correct.
Okay, well, now that you've explained it in that way, it makes sense.
Good. Okay. So this should also make that quiz a little bit easier because now you know how to look through the resources in the text to find that information, right? And I will say those appendices and then the example table, table 7.3 in the reading, they're only giving us small parts, right? So I could ask a question with a pressure and temperature that's not on the steam table you have a copy of, because steam tables are actually expensive to buy the whole thing. There's groups that make them, and to get a copy of them, you have to purchase it. We typically don't. So we're just using a small portion, right? This is not every single temperature and pressure that exists for water as a steam or a subcooled liquid, right? So the quiz questions should be from information that's actually available in our small selections in the textbook. Does that make sense?
So you're saying that the quiz question should not have required us to go to the appendix?
Oh, no, it should. I'm saying that the appendix does not hold a complete and whole steam table. It is a portion of a steam table. So
Okay.
it's possible that you might have a system that you're looking at some point, and if you go back to this textbook, that pressure and temperature aren't in the book. I'm not going to ask you a quiz or test question that doesn't use resources you'll have available to you.
Okay.
So what I'm saying is you don't have to find a different steam table. If you have the textbook, the sections that are reprinted here for you to use are what I'm going to use for questions. Does that make sense?
Can we use the book on the test next week?
If you need a steam table, I'll make sure it's printed out with the test. So no, you can't use the book.
A one-sided crib sheet, right?
Yes, you can have a one-sided sheet. Before we move into talking about the test, which is the next topic, does anyone have a question on that example or how to get to the steam tables in the book and what kind of information you're looking for in a question that tells you which steam table to use?
Yeah, I got a quick one.
Yeah.
What cued you to assume that the water was subcooled?
So when we look at the temperatures in that example 7.5, it's in Celsius, right? What temperature does water normally boil in Celsius?
100.
Right. And what temperature is our water, liquid water, coming into the core at?
What did he say it boils at?
Forget.
It's coming in at 295, right? So significantly higher temperature than it would normally be already steam. Subcooled water is water that is still liquid water at a temperature that it should be a steam, right? So because we see that it's liquid water, we know that it's being kept a liquid by that pressure. So we know from the definition of saturated steam and saturation and subcooled liquid and saturated water, that this is still, that's going to be a saturated water because of the temperature that it's still a liquid at. So essentially, because in the question, it specifically tells us that we have liquid water, not a water steam mixture or saturated steam or superheated steam. We know that because it's at a temperature that normally it would already be a vapor, right? It would already have boiled, but is still a liquid, that we're dealing with a subcooled liquid.
Right on. Thank you.
Okay. Questions on this example? Okay. And let's talk about the exam. I posted a review guide. So let's take a look at that. Okay, so first we have a list of definitions, right? It's a pretty long list, but a lot of them are pretty easy definitions. So I would definitely be familiar with what these different definitions are, okay? And they are all in the DOE handbook or both the DOE handbook and the textbook reading. The textbook does have a handy little index at the back. So if you're looking for the definition of like critical point, you can open up the appendix and it tells you that point is on page 983. And then you can flip there and it talks about critical point and your liquid vapor mixture. And there's also critical point shown in the presentations and it's in the DOE handbook. So all of these we've gone over. You've either read them or we discussed them specifically in class. Okay, we talked about the Carnot cycle, right? So, a question might be, if I give you the temperature of the heat sink and the heat source and the amount of work that's done, can you determine the amount of heat that went into the system, right? So from this PowerPoint, right? Let's look at the Carnot cycle. Right? So if I give you the temperature of the hot leg, the source, and the temperature of the heat sink, the cold leg, we have this relationship between the heat energy going out and the heat energy going in, right? And we can tell work right here on your review sheet is the equation that relates all of those, right? So we've got our work over our heat in, which equals the efficiency, which is one over the temperatures. And if I gave you a hot and a cold temperature, and I said how much usable work, so this W, was done by the engine, and that the designer of this Carnot engine had such and such efficiency, would you be able to tell me how much thermal energy the working fluid has to bring in? So solve for this. And if I asked you if this system could really exist, would you be able to describe why or why not? So for the Carnot cycle, can this type of engine or cycle ever really exist?
You said no.
No, that's correct. Why?
I don't know that.
Well, it doesn't account for energy loss. It's preserves all energy, which doesn't happen due to friction and other vibration losses and transfer through the boundary.
Exactly. It's essentially a perfectly reversible process does not really exist. And the Carnot cycle is an example of a perfectly reversible engine. The only thing that matters is the temperature on one side and the temperature on the other. All of the things that James just listed, friction and other losses, doesn't exist. So if I ask you about a Carnot cycle and have you do some calculations and then have you tell me, could this really exist? What essentially you're showing is that it's a reversible process. This efficiency could never actually be achieved by a real system. Okay. Then we're gonna have some questions about property diagrams and phase change. So if I asked you to draw a example PT diagram for water and tell me what units should be on the axis and what the saturation curve would look like, what I'm looking for is something this that we over in class. Right, so here's a PV diagram. Here's a PT diagram, right? So you should be able to put temperature and pressure. You should be able to show a triple point and a critical point and tell me what phases are happening in each section, right? I will tell you that I'm not going to ask you guys to do the 3D ones. That's too much drawing, but I might to draw a 2D one and tell me where you can find saturated liquid or where you're going to find a solid, and then what the phase changes are going between those, right? So if you have a diagram up and I tell you to show me where fusion is happening and where freezing and melting and all of those are, you should be able to show that information. Then here we're just a couple. So if I ask you to draw it, could you draw it and label it? If I give you a drawing that isn't labeled, could you fill in the labels here, right? And show me which substance is in each region, okay? Different thermodynamic systems, right? Isolated, closed, open. Could you describe what the energy and mass are doing in each system? Have a closed system. Is there transfer of energy?
Yeah.
Or and is there transfer of mass?
No.
So let's pull this up. Yes, right? So right here, this this set of slides. Closed system, no transfer of mass, but there may be transfer of energy. And we had an example of pressure cooker, sealed and insulated gas tank, a thermos, or BWR system. And then we talked about isolated systems, open systems. So being able to essentially draw this and show me whether or not heat and matter are transferring or not. Okay. Okay. Then we talked about properties of state and intensive and extensive properties, ones that depend on the mass of the object or not, right? And being able to give examples of those and explain why they're intensive and extensive. Understanding temperature scales and conversions between them and what it means to have absolute zero and why we want a temperature scale that might start at absolute zero as a zero instead of as a negative, and just kind of be able to conceptualize that. Using the equations in the DOE handbook for potential or kinetic energy, being able to define those and make calculations. It will not be open book, but you can have a formula sheet.
So is that just formulas, or can we write notes on it as well?
You can write notes on it. It can have whatever you want on one sheet of paper.
One side, one like the whole sheet of paper, both sides, or one side?
One side. Okay. And then we have some calculation questions, okay? So being able to determine different parameters of a fluid as it passes through some system component, okay? And I gave a selection of example questions. We did a couple of these in class. There's a couple that are from examples in the textbook. But for example, if I want you to calculate entropy, and I say that steam is going to enter the nozzle of a steam turbine, and you have a velocity, pressure, and temperature, and that velocity can either be mass flow rate, or I can tell you how big the nozzle is, so you know how much mass you have. And then you have the pressure and temperature at the outlet. Could you calculate entropy based on that? This example B, for example, we did this in class, and this is the one that everyone had trouble with the unit conversion at the end, right? We've got how much heat is being removed from a fluid. If you know the temperature, it enters the core, leaves the core, how what the flow rate is through the core, and the specific heat of the fluid, right? So if we had water at a given pressure and temperature, you should be able to look up specific heat if I give you a graph, or I might just tell you the specific heat of a few fluids on the test, and then you can pull that up. Determine the required flow rate in a condenser. So very much like the calculation we did for B, but instead of telling you the mass flow rate, I'm telling you how the temperature and pressure that it enters, and that the cooling water is at a certain temperature and the outlet temperature has a certain maximum. And then I'll give you that enthalpy, and you can tell me how that mass flow rate has to be to make that cooling occur at the two temperatures, right? How much energy needs to be added to a system to convert the entire system to a saturated liquid? So this is talking about specific heat of, in this case, going from a liquid to essentially saturated, so just before it does that phase change, right? And then the internal energy, pressure, and specific enthalpy, inlet and outlet temperatures, and mass flow rate. Could you calculate the joules of energy removed? Which again, this is very similar So what's happening in that example B that we did in class a few weeks ago. And I am not sure, did we post the video from that? I don't think we ever posted that. So I can post that video from when we did that example so you guys can review going through that kind of calculation if you'd like to. I'll put that on Moodle. I'll put the video on the day that we talked about it, not under the exam. So you'll have to go back up to a previous day on the Moodle to find that video, but I'll post it and I'll send you guys a message when I post it. I should be able to do it right after the class I have after this. Okay, that kind of gives you an idea of the topics that I'm going to put on the test. I think that I might have just skipped one important one, which is being able to understand why the phase change happens per the graph we looked at, where energy gets added and then there's plateaus. Let me show this real quick. Explain this temperature versus energy input, right? That example question where it asks you to calculate how much energy you have to put in to take it to a vapor. Question D, that's essentially calculating this energy input, right? That takes it from saturated liquid. So understanding this graph and what it means and what's physically happening with our phase changes. Okay, I know we're almost at the end of our time period, but does anyone have a question they want to ask real quick?
Something I'd like to bring up is we were supposed to discuss that enthalpy of ice problem during this session. It's what I remembered, but maybe we'll have to put it off a little.
Yes, we'll have to get back to that. I'm not going to put anything like that on the test. We do still need to go over that, but there won't be a question like that on the test, and we'll make sure we go over that and make sure everyone's on the same page, and I'll still give you time to revise that, but we'll not introduce that today because we're already at the end of our time.
I have another question that's unrelated, if you don't mind.
Sure.
You sent me an email that said that quiz question was a typo.
Yes.
Okay, are you going to give me the point for it?
I think that you still had an incorrect answer, right?
Well, I did, but if there hadn't been a typo, I would have seen that all three of those were incorrect, and I would have marked all of the above. Because the difference between here, let me get back to the question, please.
Joe, I will have you send me an email. Just explain that you understand. I have another class that starts right now. Just
Okay.
an email saying you explain it, and yeah, if you give me an explanation that says you understand, I'll give you the point.
Thank you.
Okay. All right. Thank you, guys.